everybody for being here on Friday afternoon in particular. So yeah, as Giovanni said, now I wanted to talk to you about HATHOR. That's the deployable heat shield architecture that we've been working on at Imperial over the past few years. And I've joined the group and this project in particular less than a year ago. So today I'll be presenting some of my work, but also some of Lisa's work and some of Danielle's work as well. And yeah, so today I wanted to talk about these few things. So first I wanted to talk about the type of missions that we're looking at and what are the requirements of these missions and how we can meet these requirements. And then I'll talk about how we design a successful deployable aero-decelerator. So I'll be talking about how we model the free stream conditions, how do we characterize its aerothermodynamic behavior. I'll talk about how the aeroshell deploys and retracts, and then how we can and we should assess stability. And then I'll briefly summarize what our plans are for the next year or so. Right, so before I go into the details of mission types and aeroshell requirements, I wanted to briefly give you an overview of an EDL event. So EDL is composed of entry, descent, and landing. And entry is the first part of an EDL event that you can see here. And so normally that happens when a spacecraft transitions from space to the atmosphere of a planet. And it starts with really, really high velocities of the order of a few kilometers per second. And then they reduce by 1 or 2 orders of magnitude as the body is in the atmosphere. And typically that's when we experience really high heating levels and high dynamic pressures, and that's why we need a heat shield, and that's the phase that we're mostly working on. And then the second phase is descent, and it begins when the vehicle has decelerated sufficiently, so its velocity is fairly close to its terminal velocity. And that's when we employ some additional elements, for example, subsonic or supersonic parachutes or retropropulsion as well. And then landing is the last phase, and really we just aim to ensure a gentle touchdown with landing. And although HATHOR, that's our deployable aeroshell, could be a very useful and a versatile option for many missions, for different maneuvers, today I want to focus on Mars. And so here where you can see at the top, so I'm showing from 1960s most of the missions to Mars, and I'm showing what the mission aim was and whether they've been successful or not. And what I think is quite interesting from this plot is that you can see that since 1971, that's when the first robotic lander touched down on Mars, actually over half of the missions trying to land on the surface of the planet have been unsuccessful. And there's actually a very good reason for that. And landing on Mars is really difficult and really challenging because there's a combination of a very thin atmosphere, because on Mars we have densities that are less than 1% than we would see on Earth. But also there's a quite decent gravity. So obviously you can see that the combination of the two is not going to be beneficial for trying to land something on there. And then what you see at the bottom is the mass of the landers. And although there has been some variation in the past, you can see that the mass has never exceeded 1,000 kilograms. And that's pretty important. And I'll come back to this very soon. And here you can see for some of the successful missions, you can see what the maximum aeroshell diameter was. And you will see that it's always been below 4.5 meters. And there's also a very good reason for this, because it needs to fit inside the launcher fairing. And this is Ariane 5, and the internal diameter of the launcher fairing for Ariane 5 is 4.5 meters. And that's really pretty much the maximum that's out there. There's Falcon 9, that's 4.6, but that's always that same order of magnitude. And so this is kind of a summary of the 20th century Mars entry vehicles with a relatively small mass, below 1,000 kilograms, and also a relatively small diameter, so within 4.5 meters. And so looking forward, if we are thinking of future human missions, then everything needs to be scaled up. And now the mass needs to go up to about 50,000 kilograms. And to be able to decelerate something like that, we need at least a 16-meter diameter. And obviously, you don't need me to say that rigid landers would be too big. They would never fit in the launcher fairing. But luckily, we do have an option, and that would be to use deployable landers. So deployable landers would be stored inside the launcher fairing, and then they would deploy before entry. And in that way, hopefully, they can create enough of a surface area to be able to decelerate the lander. And that would be for future human missions, but also for large robotic missions, so larger than what we've been able to do so far. And before I go into the details of how we design a deployable aeroshell and the specifics of HATHOR, I want to talk about what needs to change and why we need a deployable aeroshell and why we have no other option really. And so to do that, I want to introduce the concept of ballistic coefficient. So ballistic coefficient is really important in the context of entry vehicles because really what it summarizes is how heavy a body is and also how aerodynamic a body is. And to kind of understand what that means, the terminal velocity of a body tends to be proportional to the square root of ballistic coefficient. And so a heavy, compact and aerodynamic body that has a high ballistic coefficient tends to also have a high terminal velocity, which kind of makes sense. And here you can see the trajectory, so altitude against velocity, over a range of ballistic coefficients, so increasing from top to bottom. And you can see that as we change ballistic coefficient, the trajectory changes quite a lot as well. And to put some numbers to that, we can see for a range of lander masses between 1,000 and 100,000 kilograms. You can see for two ballistic coefficients, so a fairly low ballistic coefficient of 10 and a medium to high ballistic coefficient of 150. You can see that changing requires aero-decelerator area and aero-decelerator diameter as well. And you can see that with a higher ballistic coefficient, we need a significantly smaller area or diameter. And so the obvious question is, can we just increase ballistic coefficient if we want to increase the mass? And the short answer is no, but I'm going to talk you through that. So the main problem with high ballistic coefficient missions is that transition from entry to descent can become problematic. And why is that? Because if I look at what happens during descent, so as I've said before, normally we use some additional elements during descent, for example, retropropulsion or subsonic or supersonic parachutes. But here you can see that actually you need some conditions. So you need to be within some flight envelopes to be able to deploy parachutes, to be able to use supersonic retropropulsion, for example. And so you can also see that as ballistic coefficient increases, so for example, the highest values down here, actually we might not pass within these flight envelopes. And so we might not be able to use these elements. And obviously we couldn't sustain landing at 300 meters per second. But there is a way around that, and that would be to introduce a lifting trajectory. So what we could do is we could intentionally introduce an asymmetric weight distribution, and that would introduce a lift force that would change the trajectory, as you can see here. And so you can see that the vehicle would descend more slowly. It gives more control over the amount of time that it spends at the different altitudes. And ultimately, it also reduces the terminal velocity. And if we zoom in on the descent phase again, you can see that now, although the ballistic coefficient is really high, we actually can meet the conditions for parachute deployment and retropropulsion initiation. However, sadly, we have another problem with that, and that's heating. So here you can see alongside the trajectories, we can also see heating contours. And you see that in particular for the, well, as we increase ballistic coefficient, we increase heat flux as well, in particular in this region here, which is peak heating. And so when I talk about heating, first of all, I mostly talk about convective heating. And that's because there is a component potentially of radiative heating as well, from the hot gases to the aeroshell, but that tends to be negligible for the velocities that we talk about for Mars entry. And so from this slide, you can see that actually keeping a relatively low ballistic coefficient in the context of high payload mission makes sense, because first of all, it would reduce peak heating experienced by the aeroshell, and also it leads to deceleration at higher altitudes, and you can see up here. And so that could allow landing at higher surface elevations, or also the extended time available for entry would allow for guidance maneuvers, and so for to achieve a more precise landing. And so now that we've seen that we do need to keep a fairly low ballistic coefficient, we can go back to deployable landers. So if we want a low ballistic coefficient, but a high payload, so a high mass, we need to increase the surface area. And to do that, we could use a deployable aero-decelerator that is stored during launch, so it fits in the launcher fairing, and then it deploys before entry. And in the past, both inflatable and mechanically deployable aeroshells have been proposed. And so both of them, so they have, so both inflatable and mechanically deployable aeroshell have their own advantages. Mechanically deployable aeroshells in particular, they tend to be more resistant to impact. They're capable of deployment testing and restorage. That's really important because, for example, one option could be to deploy them not right when we get to Mars, but to test them before and then store them again, but at least we know that it's going to work. And also they could withstand a dual heat pulse. So they could be used for aerocapture and entry, for example, or descent and landing. And also in some cases, it's possible to use the deployed elements for landing gears as well. And so that would reduce the overall mission mass. However, in both cases, so the mechanically deployable aeroshells that have been proposed and the inflatable aeroshells that have been proposed, in both cases, most of the concepts are in the early design phase only, with little hardware development and not much further progression. For the mechanically deployable aeroshells, in particular, ADEPT and Irene, in recent years, they've moved from the concept phase to hardware development and testing. But in all cases, all the concepts that have been proposed, they have flexible thermal protection systems. And while flexible TPS is great at reducing mass, which is obviously very critical for aero-decelerators, that their behavior is not fully understood, and so it's somewhat unpredictable. And that's the reason why we've decided to focus on a rigid, mechanically deployable aeroshell instead. And here you can see deployment of HATHOR. And so we've been working on HATHOR, as I said, over the past couple of years. And the main advantage in comparison with the flexible configuration is the fact that, as you can see, it locks into a predictable geometry when it's fully deployed. And so that makes it very attractive for multi-use applications, for controllable deployment and repeatable testing. And as you can see, the panels have a structurally optimized folding pattern. And that is really important because that's what ensures both compact stowage, but also repeatable deployment. And I'll talk about this folding pattern in a bit. But first, I wanted to mention the aeroshell requirements. So these requirements have been defined considering a feasibility study by NASA, and that's in the context of human payload missions to Mars. So as I said, we're looking at a total mass of about 50,000 kilograms. And so to achieve that for Mars, we have a cone half angle of about 70 degrees. That's what was been used in the past. And that's a good trade-off between, on one side, high drag and heat transfer away from the spacecraft, and on the other side, maintaining adequate stability. And then, as I've already mentioned, we want a stowed diameter of 4.5 meters, and that's considering the constraints of the launcher fairing. We want a deployed diameter of 16 meters, and that's mostly to achieve the conditions for supersonic retropropulsion initiation of a Mach number less than 3.5 at a height greater than 3 kilometers. And then the minimum number of ribs, we've set it to 8, and that's because as we reduce it even more, the projected surface area reduces, and that reduces the drag coefficient and so the aerodynamic performance of the aeroshell. And in particular, we've selected 12 for HATHOR. So now that I've kind of given you a bit of a background and an overview, I'll talk about how we design a successful aero-decelerator. And the first step is to have a trajectory simulator. And for that, we need to model first the Martian atmosphere. And there are a lot of possible atmospheric models that we could have used. And actually improving and refining these models is a topic of ongoing research. And here I'm showing the Mars Climate Database. And so this model is quite a sophisticated 3D atmospheric model that can provide atmospheric conditions for any 3D position and time. And if that's the entry interface, so you can see that the Mars atmosphere is mostly composed of CO2. In particular, below 100 kilometers is over 95% CO2. And then, so as I've already said, the atmosphere of Mars is really thin. And in particular, above 50 kilometers, there's pretty much no density. And then below 50 kilometers, density increases almost exponentially. Oops. And temperature increases almost linearly. And here you can see a contour of temperature on the Martian surface. And you can see that there are some small variations due to location, and then there will be some variations associated with season and on a daily basis as well. And because the Martian atmosphere is so thin, actually daily variations are a bit larger than they would be on Earth. And then once we can model the atmosphere, so Lisa has developed a 6 degree of freedom trajectory simulator. And so for a 6 degree of freedom model, we need to balance forces and moments that act on a body to be able to determine its dynamics as it enters the atmosphere. And so here you can see a lot of equations. I'm definitely not going to talk about these equations, but just to give you an idea of what we're looking at. And then she used a numerical solver in MATLAB to integrate these equations of motion from the initial conditions. And so these are some typical trajectories. And she's validated the code against some actual mission data. In this case, I'm showing Spirit and Phoenix. And so you can see, first of all, that there's a very good match between the actual data and the model. The error is below 5%, but also I want to say that the exact starting conditions and mission parameters are not usually stated very well in the literature. And so that it's likely that that's what's caused some of the differences here, for example. And so actually it's possible that Lisa's trajectory simulator is even more accurate than it will look like from these plots. But also she is correlated her trajectory simulator by comparison with an industrial trajectory simulator. So the key thing was that Lisa's code is using modified Newtonian theory to estimate surface pressure. And that's an approximation, that's an approximated approach that is often quite good at hypersonic conditions. It wouldn't work very well for transonic or supersonic flow, but it's fairly accurate for hypersonic flow. And so it assumes that when the flow hits a wall, it turns immediately parallel to the wall. And so that means that we can actually determine surface pressure on a body, just considering its geometry and the direction of the velocity vector. And so that's an approximation, and that's not normally used in industrial trajectory simulators, as they use a database of aerodynamic coefficients instead. And while that's potentially more accurate in some cases, that also constrains the range of shapes that we can use, because obviously we need to use a shape that has an associated database of aerodynamic coefficients. And for example, we can't replicate it for a deployable aero-decelerator because it's too complex. And so what Lisa did to compare her tool to the industry trajectory simulators, for example, the one developed by Ariane Group, is instead of using Newtonian theory, she's introduced the database of aerodynamic coefficients into her tool, but in this case for a rigid sphere-cone geometry, so not for the deployable Aeroshell. And you can see that it compares really, really well. So the error is way below 1%. And so that's really promising because not only it shows that we can replicate results from these industry tools, and it gives confidence that we can actually use this trajectory simulator to assess the performance of HATHOR, but also it's showing that in a way, her trajectory simulator is also more powerful than the industry tools because we can replicate any shape. We can test a deployable aero-decelerator that has a novel geometry, really. And so now that we can get the free stream conditions everywhere on the trajectory, I'm going to talk about the aerothermodynamic characterization of HATHOR. And the first thing that I want to point out is that the geometry of HATHOR is significantly different compared with the more traditional sphere-cone geometries. So while the sphere-cone geometries were nice, smooth, axisymmetric geometries, now we have a faceted geometry. And that means that not only we don't fully understand its aerothermal behavior, but also we need a bespoke tool to assess it. And so we could have used experiments, CFD simulations, or engineering models for this aerothermodynamic characterization. However, in experiments, the flow conditions can't be replicated accurately. And also, if we need to do design iterations, they would be very time consuming and very expensive. So that makes it quite difficult. For CFD simulations, so we don't have the problem of simulating the right conditions because obviously we can set whatever we want in CFD. But once again, we will need quite prohibitive resources for rapid and accurate CFD simulations, especially if we want to consider a range of designs and a range of operating points. So we're left with engineering models, and engineering models, they rely on theoretical and empirical relationships to describe the flow physics. And they are a really powerful tool because they allow for rapid and reasonably accurate predictions of the properties of the flow. And so once we get the properties of the flow, we can also get the aerothermal effects and the heat shield. And the key thing is that they have a very short computational time. And so that's particularly useful during the conceptual design phase of HATHOR. And several industry standard codes exist. And the most widely used probably is CB-Aero, but unfortunately we had no access because it was only available in the United States. And so that's why we had to create our own tool, the Hypersonic engineering model for rapid aerothermal analysis of 3D bodies, or HIT3D. And I'm not going to go into the details of it. I'm not going to show any equations today, but I wanted to give you an idea of what's behind HIT3D. So in brief, it's a robust engineering model for the rapid and reasonably accurate aerothermal analysis of general 3D bodies. And when I talk about general 3D bodies, I mean that they don't need to be axisymmetric anymore. And first of all, we've used a streamline tracing algorithm to determine the surface streamline pattern on the Aeroshell. Then we've used modified Newtonian theory for every streamline to determine the implicit solution. And then we've used a range of empirical engineering relationships to approximate the boundary layer flow, and that includes an entropy layer model as well, and to estimate heat transfer rates. And then we've determined the final temperature by radiation equilibrium. And here you can see for every streamline, the surface, laminar and turbulent heat transfer rates. And then we can put everything together and obtain some contour plots. And first of all, I want to say that although this is an approximate analysis, you can clearly see that we can pick up some quite important and pretty interesting features that are associated with the faceted geometry. And I'm going to talk about that in a second, but first I also wanted to say that although today I'm showing results at 0 angle of attack, actually with HIT3D, we can model arbitrary incidents without any problems. And by comparison with some existing experimental results, but in this case for sphere-cone geometry, we've seen that accuracy of HIT3D is about 20%. And considering the accuracies of even way more complex CFD codes for this application, but also considering the experimental uncertainty, that's actually a very good accuracy. That's definitely a reasonable accuracy for what we need, especially for the design phase. But also, as I said, the other key advantage of HEAT 3D is the short computational time, which is only a few minutes on an ordinary computer. And so the short computational time, together with the reasonable accuracy, make HEAT 3D very useful during the design phase of HATHOR. And I'm now going to show a couple of examples. So I've used HEAT 3D in conjunction with the 6 Degree of Freedom trajectory simulator developed by Lisa. And in that way, I was able to get the free stream conditions everywhere on the trajectory. And then I could input these conditions into HEAT 3D and get laminar and turbulent heating everywhere on the trajectory. And so here you can see that as time goes by, both laminar and turbulent heating increase, and they increase up until peak heating that happens at about 90 seconds, and then they decrease again. And I just want to say a couple of things about this peak heating condition. So that's been determined considering stagnation point heating as determined from the Saturn-Graves correlation. And although that's considered peak heating, you can actually see that there are quite significant areas on the aeroshell with greater heat transfer rates than the stagnation point. And that's associated with the faceted aeroshell geometry. And that means that to properly size the aeroshell, we can't just look at the stagnation point heating, but we actually need to look at heating everywhere in the aeroshell and really understand what's going on in these regions in particular. And I'll now show some of the results from the preliminary design phase of HATHORs, in particular looking at its aerothermal characterization. And because we're interested in the worst case scenarios, I'll consider what happens at these peak heating conditions that you can see in this table here. And because predicting laminar to turbulent transition is really challenging, in particular for entry problems, at this point, we're not aiming to predict laminar to turbulent transition. And in particular today, I'll mostly show laminar heat transfer contours, but actually we've seen that the same trends also hold for turbulent heating. And in particular today, I'll talk about what happens at the interface between the ribs and the TPS panels, the impact of rib width, and what happens at the interface between the fixed nose and the deployable drag skirt. And I've considered two main designs. So the first one has rectangular ribs, and that means that we have sharp edges between the ribs and the TPS panels, while in the second case we have rounded ribs, so the top surface of the ribs has been curved, and now we have no discontinuities between the two components. And if we look at the laminar heat transfer contours, first of all, in both cases, we can see a general trend of enhanced heat transfer rate in the vicinity of the ribs. But with sharp edges, we see a low heat region on the ribs and heating spikes on either side of the ribs. And that's associated, so the heating spikes are associated with the slope discontinuity of the streamlines that transition from the ribs to the TPS panels. In fact, we know that when we have sharp corners, that leads to rapid flow reacceleration, to thinning of the boundary layer, and so enhanced heating rates. And conversely, we see that with rounded ribs, we now have a much more favorable heating distribution with a more uniform high heat region around the ribs. And so having seen that with rounded ribs, we get a more favorable aerothermal behavior, I'm now going to talk about the impact of rib width. So I've considered a range of geometries, a range of rib widths between 8 and 48 centimeters. And here I'm showing three designs in particular. So I'm showing the narrowest case, the widest rib, and then one design in between. And you can see that in the narrowest case, we get heating spikes again. Although the ribs are smooth, we get heating spikes again. And to understand where that's coming from, here I'm showing the streamline distribution in the vicinity of a rib. And I'm showing with dashed lines the profile of a rib, the top view. And you can see that in the narrowest case, the narrow rib is virtually equivalent to a sharp edge. And I've already shown in the previous slide that sharp edges lead to heating spikes. So it's not such a surprise anymore. And then we can see that as we increase rib width, we get a more and more gentle streamline curvature. However, if we go to the widest rib case, as you can see here, we get a more extensive region on the aeroshell where the streamlines are curved. And that leads to a more extensive high heat region. So when we're designing HATHOR, we need to take that into account and consider whether that could lead to any problems. And then finally, I'm talking about, so I'm going to talk about the interface between the nose and the drag skirt. And that's a really important region because that's at the interface between an axisymmetric geometry on one side, and that's the nose, and a faceted geometry on the other side, the drag skirt. And so if we want a smooth interface, we need to be really careful with the design of this region. And today I'm showing the sensitivity of laminar and turbulent heat transfer rates to the length of this interface region. And you can see, and that's along the center line of a panel, so as indicated by this green line here. And you can see that as this interface region becomes narrower, we're getting increased heating rates, in particular in the outer part of the nose here. And as in the most extreme, in the narrowest cases, we get heating spikes as well. And although we need to take into account other considerations as well, it's highly likely that heating spikes in this region at the interface between the nose and the panels are going to be very undesirable. So we might want to choose a slightly wider design. And so although obviously in the design of HATHOR, we're going to have to take into account a series of additional considerations, for example, to do with material choices, with structural behavior of HATHOR. Hopefully today with this rapid analysis, I've shown you that even with a rapid aerothermal analysis, we can get a pretty good insight into the aerothermal behavior of HATHOR. And so this approach is actually really useful in making the early design choices. And so far, while I've talked about HATHOR, I've really talked about it in its fully deployed configuration. And I've really treated it as a rigid geometry fully deployed. And so now I want to talk about what happens as the aeroshell deploys and retracts. So really its behavior in between these two conditions, the fully deployed and the fully retracted condition. And that's the work that's been carried out by Danielle over the past couple of years. And so, first of all, what are the requirements of the deployment system? It needs to enable the robust, predictable, and repeatable deployment and retraction of the ribs. Then the panels, they need to deploy symmetrically, and that's to minimize unnecessary material stresses. And when it's fully deployed, the ribs must retract to vertical, and that's to minimize the stored volume and so maximize the payload volume. And you can see the chosen heat shield architecture, which consists of TPS panels in between retractable ribs. And the deployment of the ribs, well, deployment of the aeroshell in general, is controlled by an actuated ring. And as the ring moves up and down, a series of ribs and struts rotates around the aeroshell main body. But how exactly? So you can see, looking at the geometry of the panel, you can see that it's a pretty different geometry between its stowed and deployed configuration. So how exactly does it transition in between the two? And as you might have guessed from the name of HATHOR, we've chosen an origami-inspired folding pattern. And first of all, what are the design objectives? So as I said, the panels need to deploy uniformly to avoid any material stresses. And that's achieved by applying a symmetrical fold pattern. They need to stow flat to minimize stacking height and minimize stored volume in general. And then they need to be fully tensioned when the ribs are rotated by 70 degrees. And that is really important because, as I've shown you before, even small geometric imperfections and sharp corners, they would lead to significantly increased heating. And obviously, we don't want that. But because we can, so by determining the exact position of the ribs, because we know that then HATHOR is always going to deploy in the same way, then we can ensure that the panels are flat when fully deployed. And so given that the optimization objectives were to minimize the number of folds and maximize the angles between each fold. And that is the fold pattern that we've obtained. And of course, it's going to change as we change, for example, the number of ribs, but it's always going to have that same basic shape. And right, so for now, essentially, we've determined this 2D fold pattern, but considering the fully deployed, once again, and the fully stowed configuration. I'm now going to look at the dynamic behavior of the system. And for that, Danielle has set up some dynamic rigid multi-body simulations in MATLAB Simscape. And that was to fully understand the dynamic deployment of the system and also to ensure that we could actually really get controllable and repeatable deployment of HATHOR. And so, yeah, as I said, that was in MATLAB Simscape using an explicit ODE solver and variable time step. And every sub-panel, as you can see here, was modeled as a rigid body with, and they were joined together using a hinge with a 1 degree of freedom, 1 rotational degree of freedom associated with a stiffness and damping coefficient. And so here you can see the block diagram that generates this 3D mechanical model. And so there are obviously several design parameters that might influence the panel deployment. And it was found that the two dominating parameters were panel thickness and the number of ribs. And in investigating panel thickness, we had to set an upper limit of 0.4% of the deployed diameter. And that was because past this value, the mass of the panels exceeds 25% of the total spacecraft mass. And that's already quite a lot, but in particular, if we compare with aeroshells with flexible TPS, the aeroshell contributes to about 3% of the total spacecraft mass. And so obviously rigid aeroshells, they have their own advantages, as I talked about before. But obviously we can't get such a prohibitive increase in weight because then they wouldn't be competitive anymore. And so here, that's what would happen in an ideal case. So ideally, as the ring moves up, we end up with a ring displacement of 100%. So the aeroshell would be fully deployed. And that corresponds to a hinge angle of 0 degrees when the aeroshell is fully deployed. While when the aeroshell is retracted, there would be a hinge angle of about 180 degrees in most cases. However, in practice, we saw that that wasn't always the case. And to understand that, this is a plot of final ring position. Well, once again, 100% was a full deployment at a function of panel thickness for a range of number of widths. So for 8 ribs, 12 ribs, and 16 ribs. And let's consider this one in the middle here, the dotted line that's 12 ribs. That's what we've chosen for HATHOR. And you can see that when the panel is below a certain thickness, so in this region here, the final ring position is below 100%. And so what happens? The aeroshell locks into an undeployed position, and that's determined by a locking in hinge C. And so that's essentially a consequence of varying sub-panel initial position and also their deployment rate. However, as we increase panel thickness, or also we increase the number of ribs, we can see that we can actually get full deployment. And this corresponds obviously to the ideal thickness if we consider only deployment and the possibility to fully deploy our aeroshell, because that's the minimum panel thickness that enables full deployment. But then obviously we're going to have to consider other things, for example, aerothermal requirements that I talked about before. So we need to make sure that actually the panels are thick enough to be able to sustain such high temperatures. And then Danielle has also created an experimental model to see if the behavior predicted in simulations could be reproduced, and also to consider whether there were some specific properties of a physical model that weren't fully taken into account in simulations, for example, friction. And this is a relatively small model with a 40 centimeters deployed diameter, and the dimension has been chosen so that she could 3D print the parts. And here you can see deployment of the model in its upright and downward configuration. And what she observed was that friction was actually quite a big deal, and it could cause asymmetric deployment in particular if there was a subsystem with higher stiffness than another. And so it was really important that all hinges were manufactured identically. And then the other thing, so now that it's stopped deploying, you can also see that, as we've talked about just before, you can see that it's not fully deployed. And so she actually observed that locking did occur. And so if we want successful deployment, we need to increase panel thickness, as we expected. And so from that, the next step would be to create a bigger technology demonstrator with a 2.5 meter diameter. But because we want to make it as realistic as possible, obviously there are quite a few things that we still need to figure out before we can do that. And one thing that we're looking into is stability. So stability obviously is quite important for aero-decelerators, because they would be, well, obviously it's one of the key things. It would be pretty useless if we couldn't have a stable entry into the atmosphere. And so one way to look into that is to use the trajectory simulator again. And we can look at not only at the trajectory in terms of altitude against velocity, but we can look at angle of attack and pitch rate and yaw and roll rates and how they change with time. And looking at this, it looks like our aeroshell is pretty stable, because although it looks a bit oscillatory, if we actually look at the actual values, we see that the angle of attack changes by way less than 1 degree, and pitch, yaw, and roll rates are all really small. However, what got us thinking was the ADEPT test flight. So ADEPT, I don't know if you remember, but that's one of the flexible, mechanically deployable aero-decelerators that I've talked about at the very beginning of this talk. And they've done, so Sounding Rocket 1, SR1, was the first test flight that they've done in 2018. And so they were testing 70 centimeter diameter aeroshell that was launched on a sounding rocket. It separated, it deployed at about 100 kilometers, and then it descended through the atmosphere, going through supersonic and then subsonic Mach numbers, and then it impacted on the ground. And essentially, one of the aims of this test flight was to characterize stability during entry. And what they observed that was quite unexpected was some tumbling and also an unexpected roll rates while the aeroshell was going at supersonic speeds. And the obvious question was, were these unexpected roll rates and tumbling caused by deflections of the faceted aeroshell? And that's a possibility, especially as ADEPT had flexible TPS, so deflections were potentially pretty significant. But also, even for HATHOR, it's really important to understand whether potentially some unwanted deflections of the ribs and the panels could cause a similar thing, or if just the faceted aeroshell geometry could actually be responsible for some instability. And so that's why Danielle has started doing finite element analysis. And actually, these results are really new, and so they're really fresh, and I thought I would share them with you. But bear in mind that they're quite preliminary. And so what she did was created the geometry, the mesh. She set the material properties and the boundary conditions, and then she could conduct the analysis. And that's once again a 16 meter deployed diameter with the nose with the solid nose that's 4.5 meters. And then she included that into the trajectory simulator, so that essentially at every time step, we could calculate the deflected geometry associated with that specific dynamic pressure and with those forces. And then we could use that for the analysis in the following time step. And she chose a panel thickness of 90 millimeters in this case. And these results are for 8 ribs, because they're just preliminary results. And what you can see, and it's really important, is the fact that if we compare a flexible geometry, and by flexible, I don't mean flexible TPS, but a geometry where, because of material limitations, some deflections might occur during the trajectory, and a fully rigid geometry that doesn't deflect at all, you can see that the trajectory is pretty similar. So looking at these plots here at the top, they're pretty much identical, but also the rolling moment coefficient, although it's slightly different, it's still very small, even for a flexible geometry. But the one thing that she noticed And I don't know if the videos are working. Not very happily. Let me try again. Yeah. The one thing that she noticed was that we were indeed seeing some surface deformations, and that was in particular, oops, doesn't like it that much. Let me try it one last time. But yeah, so we were seeing some surface deformations in particular towards the center line of the panels. And that kind of makes sense because that's as far away as possible from the supports, from the ribs. And actually these deformations were, so the greatest surface deformations, as you can see here, were about 18 centimeters. And given that the panel 18 millimeters. And given that the panel thickness was 90 millimeters, actually you can see that the deflections were pretty much as large as the panel thickness. And so actually this particular geometry maybe wasn't as rigid as we wanted it to be. And so these results are really important because they highlight how important such an analysis is to be able to help select the appropriate materials and the appropriate geometry for our aeroshell considering entry into the Martian atmosphere. And so to conclude, so hopefully today I've shown that rigid deployable aero-decelerators can enable higher payload missions to Mars. And I've talked about trajectory simulator, the aerothermodynamic characterization, deployment and retraction, and I've touched upon stability as well. And so what do we still need to do to progress to a higher technology readiness level? So we are, as I said, we're looking into developing a technology demonstrator that's as realistic as possible. And that's not only for show, but also to look into a few effects, for example, dynamic effects, verifying repeatable deployment and retraction. So that would actually be really, really valuable. And we're hoping to be able to test it in the 10x5. We're hoping to do some supersonic wind tunnel tests as well to also investigate stability, ideally in the new supersonic wind tunnel, if that comes. We would like to introduce conduction into our aerothermal model, because that would also help with material choice. And we'll continue with the finite element analysis to find material and geometric limits of rigidity. And so, as I said, today I've talked about some of my work, but also Lisa's and Danielle's work, and they're both PhD students at Imperial. And then this work has been supervised by Matthew and Paul. So yeah, that's the end of my talk. Thank you very much for listening. And if you have any questions, any comments or suggestions, please go ahead.